So we talked about mirrors last time and images. And you might remember that I gave you this equation that can help you to find the location and size of the image, given that you know the location and size of the object. And just as a reminder, the mirror equation relates the distance of the object to the mirror, which is called dO, the distance of the image to the mirror, and the focal length of the mirror. And the focal length, therefore, is the one all-important mirror parameter that you need to know. And it is given by the radius of curvature divided by 2. Then the magnification of the image, that is the height of the image, hi, divided by the height of the object, ho, is given by minus the distance of the image divided by the distance of the object. So with these two equations, you can always find the position as well as the size of the image. And this mirror equation is valid both for concave and convex mirrors. And the convention is that for concave mirrors, we assume that the radius of curvature is bigger than 0, and therefore the focal length is bigger than 0. And for convex mirrors, it is the other way around. Then for plane mirrors, the 1 over the radius and 1 over the focal length equals 0 because plane mirrors don't focus or defocus. One special case of the mirror equation is that parallel light gets always reflected into the focus. The mirror equation is also valid for both real and virtual images, upright images and inverted images, for objects and images in front of the mirror and behind the mirror. And if there are multiple mirrors in a problem, then you can apply the mirror equation sequentially, and the image of the first mirror becomes the object of the second mirror. And M is called the lateral magnification. And for the equation to work right, you need to be very careful with the signs for those various quantities. When you solve mirror problems, you should always draw a ray diagram as a cross-check. Even if you're going to calculate analytically where the image is going to be and what size it's going to have, first draw a ray diagram so that you know the approximate answer. Then apply the mirror equation and magnification equation. Be careful with the signs. Left of the mirror is positive, right is negative, upright is positive, and down is negative. And then check the analytical solution with a ray diagram to make sure that, that you didn't make a mistake. An example, let's assume we have a 1 centimeter high object that is 10 centimeters in front of a concave mirror, and the radius of curvature is given as 30 centimeters. So the first part is we draw a ray diagram to locate approximately the position of the image. Then B, we calculate the position of the image and the magnification analytically. So for part A, to draw the ray diagram, so we have the object given by these 2 points here, and we only draw the rays for the top of the object. And so the first ray we draw is the parallel ray. So that's ray number 1. So it goes parallel to the optical axis, which is this horizontal line here. And parallel rays get reflected through the focal point. So therefore, this ray continues like this. The next ray is the focal ray. So that is a ray that goes through the focal point. So it connects focal points with the top of the object. And those rays always get reflected parallel. So parallel rays get reflected through the focus, and focal rays get reflected parallel. So this ray, therefore, it goes to this point here and then is reflected into a parallel ray number 2. Then number 3 is the concentric ray. So that connects the center of the sphere with the object. For the center of the sphere, the normal is always given by the ray itself. Incident angle is 0 and reflected angle is also 0. So concentric rays are reflected on top of each other. So it goes in like this and then gets reflected back onto itself. And then the fourth one is the center ray that hits the center of the mirror. In that case, there's no difference between a plane mirror or a curved mirror. We actually know the incident angle, and we can draw the reflected angle, and then it gets reflected like that. So, of course, to really locate the image, 2 of those 4 rays are sufficient. But if you draw more of them, then you have increased accuracy in finding the image. So in this case, the reflected rays, they diverge, and that means that the image is virtual and behind the mirror, drawn in by dashed lines here. And so we just continue those reflected rays with dashed lines until they meet in some point, and that is the location of the image point for the top of the object. So now that we have done that, we go to the B part and calculate it analytically. So we use the mirror equation, solve for the image distance. So 1 over the image distance is 1 over focal length, minus 1 over the object distance. And the focal length is half of the radius, so it's 15 centimeters. So this becomes 1 over 15 centimeters. Then the object distance is 10 centimeters. So the second term is 1 over 10 centimeters. If we type this into a calculator, then we get that the image distance must be minus 30 centimeters. And so the analytical solution also tells us that the image is behind the mirror because this distance is negative. Moreover, it tells us that the image is bigger than the object, just like it looks like in this drawing here. And so that seems to be consistent. So now we apply the magnification equation. So the magnification is given as the ratio of minus the image distance over the object distance. Minus the image distance is plus 30 centimeters. And object distance is still 10 centimeters. So we get a magnification factor of 3. And because the magnification has a positive sign, it means that the orientation of the image is the same as the orientation of the object. So we have an upright virtual image. This happens to be the case for concave mirrors if the object is placed closer than the focal length. So if you have an object closer than the focal length, then you get a virtual image that is bigger than the object and appears to be behind the object. And that is made use of with shaving mirrors or cosmetic mirrors. Yes, yeah?
Is the focal length always half the radius?
It's always half the radius, yes.
And,
for all spherical mirrors, yeah.
Okay. And how do we know if it's, like, is there a general rule for knowing if the image is upright, virtual, or if it's real and upside down? Is there a general rule?
There are rules that you can find out either from the equation or by drawing ray diagrams. And so one of those rules is that if the object, for concave mirror, if the object is closer than the focal length, then the image will turn out to be virtual and it will be upright. While if it's further away than the focal length, then the image will be inverted and it will be real. If it's placed at twice the focal length, which is where the center point is located, then the magnification will be equal to 1. So image and object will be the same size, and the image will still be real and inverted. So there are such rules, but there are a whole bunch of them. They are not completely general because you have different rules for concave and convex mirrors. And so I don't mention all of them. But yes, there are such rules. Another rule, which we will learn later, that if you have a convex mirror rather than a concave mirror, then the image is always virtual. Yes?
How did you get ray number 4?
How to get ray number 4?
Yeah.
Ray number 4 is like the reflection on a plane mirror. So this angle with respect to the horizontal from the incoming ray must be the same as the angle with the reflected ray. And that is because this horizontal line is the normal of any mirror, whether it has positive or negative curvature or is a plane mirror. So as I said, you don't necessarily need all 4 rays. It's just the more rays you draw, the more accuracy you get where the image is located. Coming back to this example, so this is made use of for cosmetic mirrors or shaving mirrors. And the reason why it's made use of is because you want some magnification to see yourself better in a magnified view. So shaving mirrors are concave mirrors, or cosmetic mirrors are concave mirrors with a relatively long focal length, so that when you stand in front of them, you're closer than one focal length, and therefore you get an upright image that is virtual, meaning that it's on the other side of the mirror. And the image will be magnified compared to the original. And you can try that out by standing far away from a cosmetic or shaving mirror, and you will discover that you get an inverted image, so you look upside down. If there's an image, we still want to see the image, and the way our eyes are built is they can focus on distant objects, or they can focus on close objects. And distant objects, if you don't have any mirrors, they emit almost parallel rays because they're far away from us. And close objects, on the other hand, they will produce diverging rays. We are not accustomed to the situation where we have converging rays, rays that seem to come together. So if we step in front of the image of a spherical mirror, then we just see a blur, because the eye cannot focus on that. It's sort of like being more extreme than an infinitely closed object. So if you move an object very close to your eyes, you can't focus on it anymore. And this sort of is like moving the object inside your eyeball, and you can still not focus on it anymore. So virtual images can always be seen, since you can't step in front of them. They're behind the mirror. You'll hit your head against the mirror first. Let's talk now about convex mirrors. So the convention for the convex mirror is that we assign a negative curvature to it, so the radius is smaller than 0. And therefore the focal length is smaller than 0. And as I said earlier, the image is always virtual and upright in that case. And we can draw a ray diagram just like we did before. So the only thing now that we have to remember is that the focal point is on the other side. So if we draw our parallel ray, this one for example, then it will become a focal ray. And since the focus is on that side, it means it gets reflected like this, in a straight line, as if it came from the focus. Then the concentric ray gets reflected onto itself, also just like before. If we draw the focal ray from the object, then again we have to use this focal point here. We draw the line down to here, and then it will get reflected parallel, just like it was for the concave mirror. So all the formulas also still hold as before. So here I have my convex mirror, and I can now place an object like this. And you can see the image being back here. And no matter how close I move, the image will always remain upright, and it will always be smaller than the object. You only get demagnification, no magnification. And we can change the curvature of the mirror. And then the image will get smaller if I do that. Another interesting thing is if I get rid of the object and instead place a beam, that if I have a parallel beam, then all rays after they hit the mirror will diverge as if they were coming from a point which is the focal point. And that is true even if the beam is coming at if it's coming at an angle, then it will no longer come from the focal point, but it will come from a point in the focal plane. So from some point in this plane here. Let's now calculate an example for the convex mirror. So let's consider an external rear view car mirror, and those are typically convex. And let's say it has a curvature of 16 meters. And that means that we have to, for the mirror equation, we will have to assume it has a radius of curvature of minus 16 meters because it's a convex mirror. So the problem is to determine the location of the image and its magnification for an object that is 10 meters away from the mirror. And even though we had the rule that you should always draw a diagram, in this case it is difficult to do so because of the scale of the problem. It kind of looks like the ray diagram that we had just before, but it is difficult to draw it to scale. So in this case, we dispense with the exact ray diagram, and we move directly to the equation. And we again solve for 1 over the image distance, which is 1 over the focal distance minus 1 over the object distance. And since it's a 16-meter curvature mirror, that means that the focal distance is minus 8 meters. And therefore 1 over it is minus 1 over 8 meters. So we have minus 1 over 8 meters. We subtract minus 1 over 10 meters, the distance of 1 over the object distance. And we get that the image distance is minus 4.44 meters. And that means that the image is on the other side of the mirror, which is always the case for the convex mirror. And that is confirmed by this inaccurate ray diagram, which is not really for this problem. Then we can now determine the magnification. So the magnification is minus the image distance divided by the object distance, or 4.44 meters divided by 10 meters, and that means that the magnification is 0.444. So you see the car as about 44% of its true height.
Why is it negative 1 over 8 meters?
That is because it's a convex mirror, and that means that the focal length is minus 8 meters.
Because it's on the other side of the mirror?
No, it's simply because it's a convex mirror. All convex mirrors have negative focal length. So that is the convention. Otherwise, the equation will not work for convex mirrors. Of course, negative radius doesn't really make sense. So it's simply we assign a minus sign to make the equation work correctly. So that's why it's minus 1 over 8 meters rather than plus 1 over 8 meters. And the image is upright and virtual. Before we continue with refraction, I'm going to tell you the solution of the little puzzle I gave you at the last lecture. And the puzzle was, how come a plane mirror inverts left and right, but it doesn't invert up and down? And the answer to that riddle is that the mirror neither inverts left and right or up and down. It inverts front and back. When you raise your right hand, then the mirror image will also raise the hand that is on the right. It is just we imagine the mirror image being a person And then we sort of, in our head, we rotate the image around the vertical direction. But in reality, what is true is that the image has the face on the other side than the back, than the real object. And therefore, mirrors invert front and back, and not left and right or up and down. And therefore, of course, it's completely symmetric whether you tilt your head sideways or do anything like that. So now let's continue from reflection to refraction. And as a sort of introduction to that, we consider again the speed of light. So in vacuum, the speed of light is the same in all frames of reference, and it's a constant of nature. So this cannot be changed. It's always 3 × 10⁸ meters per second. Even if you move with respect to the light source, this does never change. However, and of course, there's no signal speed faster than this light speed. However, once light travels in a medium, like water or air or anything that is not vacuum, then it slows down. So the light speed is no longer constant, it's no longer this value. And how much it slows down will depend on the medium. And we can define an index of refraction which describes how much slower light will move. And that index of refraction is, or the velocity is then given as the speed of light in vacuum divided by that index of refraction. And in air, this index of refraction is very close to 1. And here's a table of index of refraction for various materials. So in vacuum, of course, by definition, it's exactly equal to 1. And you see that air, it's slightly bigger than 1. But to a good approximation, it's also 1. And then water is 1.33. Alcohol is 1.36. And the one of these largest index of refractions that you can find is diamond with an index of refraction of 2.42. So the speed of light in diamond is much slower than in vacuum, more than a factor of 2 slower. To describe refraction, we use the so-called Snell's law. So a wave that hits a boundary where the speed of propagation is different is both reflected and refracted. So we can define incident angles as usual. So we define a normal to the boundary surface. For example, we can have air and water. And we define an incident angle of the incident ray with respect to this normal. And we define, for the reflected ray, we can define a reflection angle. And for the refracted ray, we define a refraction angle, again with respect to the normal. And then the rule is, or the Snell's law is, that the index of refraction in the incident medium times the sine of the incident angle equals the index of refraction in the medium for the refracted beam times the sine of that angle. And that means that if the index of refraction here is smaller than here, that we bend the light ray towards the normal, and in the other case we bend away from the normal. And here is the reverse case where we actually have a ray coming from water into air, so we bend away from the normal. And of course, then incident index of refraction and index of refraction change positions. So we can actually do this in reality. So here I have a tank of water and a light beam that I can change the angle with. And the normal is given by this black line. And if, for example, I have an incident angle of 40 degrees, then I have a refracted angle of 30 degrees. And if I move to 80 degrees incident angle, then I get a refracted angle of 40 degrees. And you see that the refracted angle is always a bit smaller. And if I have 80-degree angle, then it's very difficult to see the refracted beam at all, because the closer I get to glancing incident, the more reflection I get and the less refraction. And we can also do the inverse experiment. So let's say I have an incident angle in water of 30 degrees. Then I get about 45 degrees for the refracted angle. Or 20 degrees incident angle gives me 30 degrees or so for refracted angle. And if I have normal incidence, then the angle is it's still normal incidence. So and the same is true if I do the reverse case. Normal incidence is not changed. So because of Snell's law, which we can also formulate in this way, if we don't like the index of refractions, we can define it in terms of velocities. And then you usually say the ratio of incident and refracted angle of the signs is equal to the ratio of the velocities in the medium of the incident ray and over the medium in the refracted ray. This law leads to a bunch of optical illusions in water, for example. For example, if you watch somebody else's legs who is halfway in the water, the legs seem way too short. And the reason for that is you assume that light travels in a straight path, but in reality a light ray coming from the foot is refracted, then it bends away from the normal. And so you see the foot here when in reality it's down there. And by the same token, you always underestimate the depth of a body of water. It always looks shallower than it really is. And anybody who's ever dived knows that that is true. So let's calculate an example with Snell's law. So let's assume we have a slab of glass, and we have a light ray that strikes the glass with an incident angle of 60 degrees. And the question is, what is the angle of the outgoing light ray after it passes through the glass back into the air? And to answer that, we apply Snell's law at the first surface. So that gives us that this angle theta A, or the sine of that angle theta A, must be equal to the sine of 60 degrees divided by 1.5, because 1.5 is the index of refraction in glass, and we assume that the index of refraction in air is 1. And if we perform these operations, then we get that the sine of theta A must be equal to 0.5774. And this corresponds to an angle theta A of 35.3 degrees. So now we observe that this refracted angle theta A is the same angle as the incident angle for the second surface, which is located here. So therefore, we know what the incident angle is for the second surface, and we can apply Snell's law again at the second surface. So this time we multiply sine of 35.3 degrees by 1.5. And if we do that, then we get 0.866 for the sine of the outgoing ray, the one that goes back out into air. And that means that theta B equals 60 degrees again. And therefore we observe that if you have a slab of material, even if it has an index of refraction that is different than that from air, it doesn't change the direction of the rays, but it parallel shifts them. So instead of the ray going like this, which it would have normally gone, it is now shifted by some distance s between the original ray and the refracted ray. This shift is actually given by this formula, if you're curious. So let's go through another example. Let's assume that a swimmer has dropped her goggles in the pool, and the pool is marked as being 1 meter deep. However, when you look at the goggles, they don't seem to be that deep. And the question is why, and also how deep do the goggles appear to be when you look straight down into the water? The answer is we consider a ray bundle from the goggles with just small angles from the vertical. So we assume that we peer directly down into the pool, directly from above, and therefore we only consider rays that deviate from the normal direction by a tiny little bit. And if we do that, then the angle theta 1, which is the direction with respect to the vertical, which is also the normal, is also the incident angle, and we can apply Snell's law, but we do it approximating the sine function with the argument of the sine function. And we can do that if the angle is sufficiently small. So in this case, theta 2 is approximately equal to sine theta 2 is equal, by Snell's law, to n water times sine theta 1 is approximately equal to n water times theta 1. So Snell's law becomes a lot simpler in the small angle approximation. Simply theta 2 equals n water times theta 1. And theta 2 is the outgoing ray once it hits the air. If we assume that the position where the ray refracts with respect to the position of the goggles is called x, then we observe that the tangent of theta 1, this is theta 1, is given by this distance x divided by the depth. So this is x over d. If we define d prime as the apparent depth of the pool, meaning if we continue those rays into a straight path, then they would meet at a point that is above the goggles. And we have a similar relation only now that we have d prime and x. So the tangent of theta 2 equals x over d prime. Now we use again the fact that those angles are small, and for small angles also the tangent function can be approximated by the argument of the tangent function. So we can say that theta 1 equals x over d, and theta 2 equals x over d prime. So now we can actually solve the problem. So d prime equals x over theta 2, so that's using this equation. And now we plug in for x this equation. So this means that we get x over theta 1. I'm sorry, for theta 2 we now apply Snell's law. That means that theta 2 is approximately n water times theta 1. So instead of x over theta 2, we get x over theta 1 divided by n water, which is the depth divided by n water, using the relation between theta 1, x, and d. And since we know the index of refraction of water, which is 1.33, the pool appears to be 75 centimeters deep, or the goggles seem to lie at a depth of 75 centimeters. So in general, if you look straight down in the water, water looks 3/4 as deep as it really is. The refractive index is a function of the frequency or wavelength of the light. So therefore, red light refracts differently from violet light. And one can therefore split a beam consisting of many wavelengths into separate monochromatic beams. So for example, these are the is the index of refraction for fused quartz as a function of the wavelength. And you see that the index of refraction is becoming bigger as you go to shorter wavelengths. And this is also true for various other materials. All of these are listed here. And if we actually make two surfaces at an angle, and that is then called a prism, we can split light of many colors, or of many wavelengths, I should say, into separate beams which have only one color. So that is also called a spectrum. And a typical example for such a spectrum is a rainbow. In the case of a rainbow, there's no prism, but we can replace a glass prism, a picture of that, for example, is shown here, with droplets of water. And if the sun is behind you, then the index of refraction in water is different for different wavelengths, and therefore red light gets, or the red light in the sunlight gets refracted differently than the violet light will be. And therefore, the colors separate, and we see bands of color. So if you're high enough above the ground, then the rainbow is actually a full circle. You can see that if you look at clouds in an airplane, for example. What you need are water droplets in the air, for example, rain. And there's actually one reflection also from the far side of the droplet. So the rainbow always appears if the sun is behind you and you're looking at, for example, a waterfall in front of you. Let's briefly discuss the difference between a spectrum and colors. So just like for sound, there are two things. There's the physical phenomenon, and there's a sensation in our brain. The latter is not just determined by the physics, but also by how our eyes are constructed. So the spectrum is produced by different wavelengths of frequencies. For the eye, however, there are three color receptors in the eye. And therefore, there are three primary colors that human beings can see. What we call color is the relative sensation of those three receptors. And in physics, we don't have three principal colors. We just have wavelength and frequency. As a consequence, the rainbow doesn't have all possible colors. There are colors that are missing, for example, brown. And also, in the physical spectrum, there's no connection between the blue and the red. While human beings, they see color on a continuous scale going from the blue into the violet and from the violet into the red. There's any shade of color is possible in between. For the wavelengths, of course, that is not possible. 400 nanometers doesn't connect to 700 nanometers. So one last remark about refraction. Since, just like for the pulse transmission that we discussed for waves on a rope, the boundary, at the boundary, the fields can only vibrate at one particular frequency. And therefore, the frequency of the waves is not changed by the refraction. And therefore, the wavelength has to change because the wave speed changes. Since the wave speed, v, is c over n, the wavelength has to be c over nf, or the wavelength in vacuum divided by the index of refraction. So wavelengths get shorter inside a medium than outside. And let's continue that thought with an example next time.